So maybe just before, so while people are sitting or not sitting, if you go on GitHub and if you check this address here, you'll find all the slides that you have seen today. Mostly, I think, are Google Slides. I think that are Google Slides. I think that Paolo has a link with the slides, and you find all the, for example, the repositories that Luca pointed out are in the slides. So you can actually go there and try his code. And you find the slides. You find the code that you will see now. You find my slides, so you can go back and check that. So just to give you an overview of what we're going to cover the last hour, what I'm going to do is, my goal is to explain you how those special TensorFlow processing unit, TPUs, are working, why we need them. I'm going to explain you briefly what is TensorFlow Lite, that is contrary to what many people think is not like a light version of TensorFlow. So what the goals are of TensorFlow Lite, and how you can make models like use less memory and less energy and be faster, so that they run on like those small devices like this one. That is actually one of those chips that Google produces, but is like a Raspberry Pi. If you work with a Raspberry Pi, you know what it is. This is kind of similar, but I'll point out the differences. And I'll show you a demo, so we'll see that just to show you how this works. Then what we will cover. What we will not cover are things like how to use TPUs on Google Cloud and stuff like that. Those are different things, very different things. So TPUs. First of all, who am I? So I'm also a Google developer expert. So I wrote 2 books, and I do I'm split between research in different fields, and I also do research in AI. We do experiments at a big insurance company in Switzerland. If you want to get in touch with me, feel free to use any of those channels. You'll find, I think, also the emails from Luca on the slides and on Paolo, so you can get in touch. So we're happy to help. And if you are based in Switzerland, not many are, but I know a few are. So we have also a Swiss TensorFlow user group that we meet regularly. Actually, this meeting was first held in Zurich. And this is actually one in Milan, because we wanted to try to bring TPUs and so around Europe. So that's why we are here. First of all, I wanted to give you a bit of context. So how many of you have heard the name TPUs, Tensor Processing Unit? Okay, so a few of you. So what are those? If you read blogs and read like what Google writes, you know that there are those kind of chips that are supposed to be very fast when doing machine learning, right? So you get like CPUs and GPUs. Now you know that those are like CPUs are kind of fast, GPUs are faster. And then there are those kind of magic chips that Google produces that are supposed to be incredibly fast. And so, but the question is that I want to answer here is actually why we need TPUs. I mean, of course, if you have ever tried to train a model and it took you like 1 week, you know that you want something fast. But the question is, for example, why you don't get faster CPUs, for example, right? The problem is that, and you probably have seen this like 2,000 times by now, you know that the Moore's law is not valid anymore, meaning that CPUs are not getting faster and faster as before, right? So we kind of reach like a plateau, right? So you get CPUs that are faster. At a certain point, they get not as fast as before in the same amount of time due to several physical limits. So at the end, this is why people started using different ideas, like we put more cores in it, right? So you have CPUs with lots of cores in it, but the problem there is that you have to have processes that can be parallelized, because if you have like a process that runs on 1 core and has to run sequentially, you can have as many cores as you want. You not get any gain at all, right? So people try to find those kind of solution and using, there are many, right? But at the end, you are constrained by the physical limit. So what can you do to do that? Because you start like when you do deep learning, and if you read like Google AI blog, they like take billions of parameters and train for weeks and thousands of GPU hours, and you wonder how they do it. And what people started to think is the following. So instead of having a CPU, right, that is something that can do everything you throw at it, right? So you can program a CPU to run a word processor, you can do math, you can do computer vision, you can do whatever you like, right? So they're general purpose hardware, right? You can program them. People started to think, well, if we develop something that can actually do just one thing, but that one thing incredibly fast, right? So the idea is that people started thinking about building stuff that actually can do just one thing. Right, so for example, in those chips, you have a normal CPU, just a plain CPU, and there is I hope it's not, okay. And you have an additional processing unit that actually, and I'll show you, that actually does just matrix multiplication, okay? So the idea behind the TPU is to start using something that just does one thing, but does it extremely efficiently, okay? Of course, you have like, before going there, you have like positive sides. Oh, that thing is really fast. And the downside is that only that thing is really fast. Okay, you cannot do anything else. Okay? And what is the operation that you actually do many, like millions of times when you do deep learning and you work with neural networks, is actually you multiply matrices, right? If you've done like, that you have like those weights matrices and you multiply by the inputs, and those matrices are so big and it takes so much time, and this is the operation that is done over and over again, okay? So, how it's working, and I want just to give you a very high-level overview for you to get an idea why it's different. They use a completely different way of handling data that is called what's called a systolic architecture. And if you read that, you'll not understand it because I'm saying that arrives at regular intervals from different direction. What does it mean to arrive from different direction to a CPU, right? So you don't have like north, south, east, and west. And I'll explain you that. But the main point that you should take away from this is that it actually can do specific operation without accessing memory. Because one of the main bottlenecks that you have in CPUs when doing those big operation is that the CPU has always to access memory. So you have the bus between the CPU and the memory, and this is the huge bottleneck that actually is the culprit that shows down everything. And just to give you an idea, before explaining you how this works, those graph tells you how much more efficient are, like in number of operations per watt, so also including the energy, like considering like GPU versus CPU, or TPU versus CPU, or TPU versus a GPU. And you can see that when you start using TPUs, you suddenly are like 80 times more efficient in energy and in performance. Right? So it's really something that makes a huge difference. And to give you a practical idea, for example, on those, we'll see if the demo is working, that depends on the network, but if you like run an image recognition demo, imagine a Tesla driving system that have to identify and localize cars in front of you, okay? So you can run a small demo where you have a video of cars traveling, and there is a network that is trying to identify where the cars are. Okay? If you run it on a CPU, of course this is slow, but if you run it on a CPU, you get kind of 2 frames per second. Not really usable in a real life scenario. Of course, you would not probably use something like that, but anyway. If you start and if you decide to run it and you write the code and run it on the TPU, it moves from 2 frames per second to 60 frames per second. So you start, so it starts to be possible, right, to build application that you can use in real time. Because of course, if you do just one inference run or whatever, is like not really interesting. But when you start doing stuff in real time, it makes a difference, okay? So, and another thing that I would like to think about, I would like to try to calculate with you how much energy you actually use when you train a network, okay? Because it seems nice, you have a network, you have Google Cloud, and you have like GPUs, right? Consider that just a CPU, okay, when it works in 24 hours, it needs 2.28, roughly, kilowatt per hour. A GPU goes up to 6, and consider a data center that can have up to 5,000 GPU, like CPU with 8 cores, it goes up to 52 megawatt per hour. And you know, like the 12 megawatt per hour can actually give enough energy to 500 houses, just to give you an idea. So when you are starting to train those big networks, you can also say, you know what, maybe we should think about saving energy for the, you know, like the, you want to make sure that like the planet stays is well and everything. So there are also considerations about the amount of energy that you have to use to do that kind of thing. Now, imagine that you transfer, I mean, this thing doesn't need 52 megabytes per hour, but imagine that you have something like that with a small battery that have to run somewhere where you don't have an outlet, a power outlet, right? So imagine that the moment that you need lots of energy, this will die pretty soon, right? So if you need to have something that is, imagine that you want to use it like in a third world country where you don't have access to electricity as easy as here, and it may be quite an issue if this dies like after 10 minutes, right? So what you want to do is you start saying, okay, you know what? It's not only like to train like BERT or those big networks in less time, it's also be able to use less energy in general and to use like things, what's called on the edge, so on small devices, right, without killing it like in a few minutes. So what are like, and I'll give more like information about edge devices in a short time. So what are, of course, limitation is that since the TPUs are basically, and I'll show you why, are basically doing only matrix multiplication and only that, okay? Of course, the moment that you have models or things that doesn't do matrix multiplication, they are completely useless. So what happens is that those operations are put on a CPU, the CPU is low again, so you don't gain anything really, right? And of course you have to have like operation and like we've seen like many things about TensorFlow, you need to have like the operation that TensorFlow has to do, like multiply matrices or sum matrices or do stuff like that, they can run on the TPU, right? They don't run automatically. Stuff doesn't get automatically put there. It's not like a hardware thing, right? So you need like, if you start having custom stuff or you have like, you know, like high precision arithmetic, and I'll explain you why, or you have like lots of access of memory, then they tend not to work that well. So the main message is that TPUs are great, but are great for specific things, okay? Again, so the typical example is image recognition, big convolutional networks, big matrix multiplications, perfect, okay? So, and now I'll try to explain you how this systolic network works because I think it's really fascinating. So the CPU, the classical way of CPU when you multiply the matrices is that you take, like, imagine that you're doing an element-wise multiplication between matrices, right? What you do, you take the first two, you multiply, and you get the result. You take the second two, you multiply, you get the result, you sum to the previous one, and you go on and so on. So it's a sequential set of operations, right? Element by element. The more element you have, the slower it is, okay? When you start doing that for like 1,000 times 1,000 images with 3 color channels and you do convolutional networks with 64 filters, it takes a while, okay? GPU is actually parallelizing the same kind of sequential operation. So you can do more of the same at the same time, okay? So, and this is why GPUs are so nice, because you can put like stuff on a GPU and you get quite a speed boost. If you use Google Colab, and you know that maybe how many of you have used Google Colab before? Almost everyone? Okay, so not everyone, I'll show you later. So Google Colab is actually a Jupyter notebook. If you wrote Python code, maybe you know Jupyter notebook, where you can actually say, I want to use GPUs. And try to train a network without and with a GPU, and you'll see a difference. You see a big difference there, without even changing the code. But that's just why TensorFlow is so nice. So again, A CPU is a sequential operation, right? So you have to do one at a time. A GPU suddenly, okay, it's cool, we can do lots at the same time, but it's still a sequential operation. You still have to access the memory, okay? So now we get to the TPU, how this works. So first of all, just the name, if you see this ASIC, is because there are these application-specific integrated circuits, okay? This is actually the one that are, like, I don't know if it's version 3 or 2, I'm not sure. This is what you have like in Google Cloud servers. This is a big one. It's not the one that we are looking at today. This is actually this one without the fan, okay? The CPU is this one. The TPU is this one. The rest is almost a complete Linux computer. And I say almost, and I'll explain you why. But it's basically, you have a Linux distribution on it. You have like USB ports. You have a HDMI port. You have like a network cable. You can do almost everything you can do with the Raspberry Pi. So TPU version, and you'll probably not understand from here, but I put that because it's a nice visualization. The idea is that you actually, the best way to explain you is the following. So let's put it this way. Imagine that this is our TPU, okay? Each of those squares are what they're called like this arithmetic processing unit, okay? Logic unit. That means that this one does one operation and one operation only, meaning it multiplies to number and keep in memory, keep inside the value, and then if it multiplies again, it sums to another one, it does anything else. And what happens is here, what you can see is that those units are not actually accessing the memory. What happens is that they are talking to each other. So they're actually connected to each other, okay? So what happens is that see that there are numbers on top and number on the left. And you remember when I say like coming from different direction? The reason is that different units get different data at different times from different directions. So the first time, at the time 0, there is nothing happening. You prepare the data, okay? So what happens is that the first time, you saw that the first number were B and A, so at the first time, step 1, this unit does nothing else than multiply the two numbers, okay? So multiply these two numbers. Now, what happens is that this number does nothing else than just flow in this direction. Unit after unit. Enters one unit, exit the unit, enter the next unit, exit the other one, and continue. So at a certain point, this number will be an input for this unit. Okay, and the same goes for this one. It goes down, and they go down one after the other. Okay, and they go right one after the other. So at time 2, this number will exit from here. Okay, this number that was here will exit here. Okay, and suddenly this unit has 2 inputs, so it multiplies this. This unit has 2 new inputs, so it just multiply those and just sum to what has in memory. Okay, now this number will flow here. I guess you get the idea, right? So it flows, right? This number flows here. Suddenly this unit had 2 inputs, so multiplies that. This has 2 input, multiplies that. Then you move on, and so each time one of those flows. When they go out here, they're done, okay? And I don't know if you noticed that if you know how to multiply like matrices, and if you look at the content of this is actually the first element of the multiplied matrix here. And you go on, right? The numbers goes in this direction, and they become input. And at the end, when you finish, you have actually the multiplicated matrix here. Okay? And what you do, or what's important is that you don't actually access memory. Okay? So those units are just talking to each other, and this, of course, this is very fast, and they don't need to transfer much information, right? Of course, TPUs are not 3 by 3; they're a bit bigger. But the main point here is this one. If you're curious, you can check what the von Neumann bottleneck is, but it's basically is what limits the CPU a lot when they have to deal with lots of data, okay? Because you will also have like this, the throughput like on the bus, so it's really what limits CPUs, right? And that's how TPUs are actually working. So, and you can imagine that they do that, and this is very fast because there is no access to memory, so it kind of it's really fast. So Of course, again, so Google, like cloud TPUs are big like arrays, and you get lots of those linear arithmetic logic units that communicate, so they can actually multiply big matrices, okay? So you have questions up to now. Is it more or less clear, the idea? Okay, so, and that seems very nice, so you can think, okay, that's nice, so we know how to use it, so Google is building up for us, and you can actually use it, okay? Now, the problem is that when you start using those kind of edge devices, okay, now to make it so small and to use so less energy than the others, and I'm sorry. I think I can close this one. Okay, so, for example, you know what computers are good at multiplying, right? Floating numbers or integer numbers, right? Integer numbers are much faster to multiply for a computer than floating point numbers. Not only that, it costs lots less of memory multiplying integer numbers than, for example, than floating point numbers, okay? So for example, this one supports only integers. So you can run models on these that use only integer numbers. And this is why Google came up with TensorFlow Lite. And I'll show you then what is used for. So think just for a second how you can train a network, define a network, let the network learn, and do inference using only integer numbers. But you don't have floating numbers. You don't have like the sigmoid between 0 and 1. It's not between 0 and 1. You have 0, 1, 2, 3, 4, just those numbers. So you get into a completely different way of doing things, and you need like other tools to be able to do that, okay? If you're interested in knowing how much more performant are, you can read the paper. It's a long paper by Google that explains you really how much energy you save, and if you want, feel free to read it. So imagine the problem of having like networks that uses only integer numbers, okay? And let me go to the other presentation. And we go over like TensorFlow Lite. So again, the same link, again, so we can skip that. Okay, so before going to TensorFlow Lite, so I wanted just to clarify what I mean with embedded device, what's something like that, right? Those devices are also, if you like work in industry and you have, for example, those terminals where you get money from, or like the one where you're a supermarket that is actually like you can scan things. All those kind of things are considered embedded device, where they typically run one single application. They typically are not an internet. Today, also a smartphone is an embedded device. We can discuss that because it's not really running one single application nowadays. But anyway, just for you to know what I'm talking about. I'm talking about something like that can be like, I don't know, you build a cat, like if you have a cat, you build like this small door for your cat with an image recognition system that opens only for your cat. There are projects, if you look on internet, you can build one, unless it fails and then your cat stays outside. So the problem with embedded system are the one that I was trying to discuss at the beginning, saying why we need TPUs. You remember I said we need TPUs because we want to save energy, right? Of course, we are talking about maybe a data center, but on those devices, we want to save energy. We have a slow CPU, and I'll show you what I mean when I say slow CPU. You may not have internet, okay? So maybe you don't have internet there, right? And you don't have much RAM. So consider a typical like a network with the number of billion of parameters. So the data set that you're using can be difficult to get everything in here, okay? So again, so we want models. So you know that when TensorFlow loads a model, you load the model in memory and then it runs it. So it should be probably small, right? A small memory footprint. Otherwise, it won't run, okay? You don't want, you know, for a computer, a CPU or a TPU or a GPU, whatever it is that you're using, every operation costs energy. And the more complex is, like using floating point 64 costs more energy than floating point 32, costs more energy than int8, costs more energy if you're using binary networks. Okay, so there are those kind of considerations in place. You don't have like a UI or user interface and you have slow computer, load stuff in memory takes forever, okay? So the question is how we can try to solve all those problems. Can we do something? And so we need to convert the models in some kind of format, right? And TensorFlow Lite is being developed exactly to try to address those points. These are the main reasons, okay? So you need something that you take a huge keras network that you have built, and you want, for example, to transform in some way to use only integers. That's called quantization. We'll look at that in a second, okay? You want to make sure that you don't have this big memory footprint, and so on and so forth, okay? So the idea is that when you are actually working with those devices, that you actually train, write a model on your development machine, your big keras for your cat image recognition door that you want to build. Then you kind of have to convert it in some way, okay, to make it small, fast, cost less energy, and so on. Then you have to copy it on this device in some way, and then you run it on this device, okay, with an interpreter that is able to profit from all the changes that or the conversion that you have done. Okay, so we want to make it smaller, right? Make inference more efficient, more fast. Keep in mind, imagine 2 frames per second, 60 frames per second, okay? Less memory, you don't want to access memory all the time, okay? And use less energy, right? And the main technique to do that is what's called model quantization, or simply quantization, okay? So the moment that you're dealing with TPUs, so you need to understand what quantization is. And I'll try to explain what it is. So imagine the following scenario. You have your weights, right? Your weights are, I have to stop doing that. Your weights are simply like floating point numbers normally that goes from one value, the minimum volume, you can call it mean, whatever is -5, -7, whatever, to a maximum value, right? And you are on the floating point scale, meaning it can have almost any value, basically, okay? What you actually do when you quantize weights is you actually project your continuous weight to a set of integers, of a discrete value. That means that sometimes you have to round numbers. So instead of going here, you don't have a number here, right? So all those numbers that are between, can you see it? Between here and here, right? So in this region, goes actually converted to the same number, okay? Those one converted to this one, this part to this one, and everything that is above gets converted to this one. So instead of having like maybe huge amount of value, you have just 255. For me, amazing thing is that networks continue or lose almost no accuracy when you do that kind of transformation, right? And thanks to this kind of property, and it seems amazing, but networks are quite stable when you change or when you quantize the weights, that actually you lose maybe a few 0.23% on famous network, and you get this kind, and you can do this kind of conversion, okay? So basically the idea is, so TensorFlow Lite, what it's doing, actually take your model, and you have these big vectors, these matrices of weights, and actually convert them from a continuous floating point set of values to values. This is, for example, integer 8, 255, and this is, for example, what this was, okay? So this is the main idea about quantization. It seems easy, right? So you convert the weights and we are done. Actually, just to give you an idea why it's more complicated, I mean, it's more complicated, but just to give you an idea, you quantize your weights. So easy. So you project that. It's just a linear transformation. I'll show it to you. You can actually, it's quite easy to understand. You can multiply with the inputs, and suddenly, when you multiply and sum many integers, what you get, you easily get over 255. Okay, if you have like, I don't know, here, you know the MNIST example, 28 by 28 and 784 elements. If every weight is like 2 or 3 and you sum 784 of them, you kind of get over 255. So the problem, you get an overflow, so you cannot simply like continue and propagate the integers because you will get overflow errors if all the numbers, the data types are integer A. So you kind of have to to be smart and say, okay, you know what, we multiply and we put in a higher bit, larger bit integers, then we rescale it down to our integer 8. So it's slightly more complicated than it sounds, right? But the main idea that you should take out is actually what you're trying to do is actually just that, right? And this is why you will probably, if you read blogs and reads like books on that, you will read about the weight quantization and activation quantization. And when the people are talking about activation quantization, the activation is actually what you apply to this w.x, you know, the sigmoid, the ReLU, those kind of function, is actually this kind of things, this kind of problems, okay? We can talk about input because, for example, this one was also the inputs to be integers. Okay, so you have questions about quantization. It's a very high-level view, but you get the idea, right? Any question about? No? Okay.
Just a rescaling.
Yeah, it's just a rescaling. It's actually this one. It's just a linear scaling. So if you know, like, to change like the minimum and the maximum and then the step. It's really like a linear function that you apply. Of course, we can, I'll point out a few things, but just that's exactly the same. Now, just for you, we will now look at the second one, but just for you to keep in mind, there are two kind of, so think about the problem that you face. What I showed you is what's called post-training quantization. I trained my model, I have my weights, everything is working fine. Okay, now I take my weights and I quantize them, right? Fine, so I've done the training. I'm not like training with integers, I'm just converting them. That's what's called post-training quantization, kind of easier. Now imagine the following scenario. You may think that maybe if I do training with integers, I maybe get better results because I'll try to keep in mind that I have integers, so it may be better than that. You can do that and you get better result. It's a lot more complicated than post-training. You need to like, you've heard like Paolo talking about the computational graph. You have to like create fake nodes. It's complicated. So TensorFlow allows you to do that, but it's not easy. The easiest thing that you can do, and it's typically for 99% typical enough, is this post-training quantization. But just that you know that there are those two kind of scenarios. Again, this is just a linear. You kind of, first of all, you get the maximum and you have the number of bits, and then you can actually just convert it. Now, just to give you another layer of complexity on what we were discussing is the following. I told you that you just scale the two, right? Let me go back for a second here. Now, typically, weights are negative and positive, right? So some way you get a 0 in here. So for example, when you quantize and when you do this linear, do you want to keep the 0 at the same place? Do you want the 0 to remain the 0 or no? What do you think? Or do you think it doesn't play any role? So if a weight was 0 in floating point, do you want it to be 0 in integer? Right? It's actually a good idea because when a weight is 0, you can actually say, I mean, it's 0. The multiplication with those weights will be 0. So one thing that you try to do, for example, is to keep the 0 at the same place. Right? So there are all those kind of minor, smart, like optimization that you're trying to do, and that means that you kind of have to choose the right parameters there. But just to give you an idea that when you quantize, you don't simply like apply without thinking, but you try to make it in a way that you optimize, and I'll show you also why. This is what the TensorFlow actually is probably easier, even easier to read. It's what you find in the official documentation. And to give another layer of complexity, you can start quantize tensors by column, by row, the entire tensor, by layer, and so on and so forth to try to find what's working better. Typically, TensorFlow Lite does it for you, but you have lots of flexibility. If really helps, it's a question of trying, but you kind of, it's also a field where there is lots of research going on. So, and just to give you an idea, now you don't have to understand the math. You can ignore the math, okay? I'll try to let you understand what I want to say. So if you imagine that A is our input, is our image. What we want, it's our input, and B is actually our, suppose that B is our weight matrix. Imagine that is this WX multiplication, okay? Now, when you do multiplication of matrices, you multiply the elements in a certain order. If you don't know which order, it doesn't matter, but imagine you know that you multiply a specific element of one matrix by a specific element of the second matrix. What sum of A and sum of B. Now, if you put in A the linear transformation, and I spare you like the math, you multiply everything and I spare you the math, you get like 4 terms. And the interesting part is that when you quantize, there are terms like where the input appears. That means if the input changes, this term will change, right? If I get a new image as an input, I'll get new values. Will change because you have the input. This is the 0 that will remain fixed as before. So this is not changing with the input, and this is the weight that is fixed, has been trained, right? So, and these are just the place of the zeros that are not changing. So already, just by doing that, I just cut into the number of multiplication that I have to do inference, okay? So just to say that the quantization, first of all, reduce like the size, and then it makes it faster, but it's also reduce the number of multiplication, meaning reduce the energy that you need. Okay? So now TensorFlow Lite, it's actually quite easy, right? So it's not the light version of TensorFlow. It's something that has one goal, and is to quantize a model to run it on like specific hardware. Okay? And the idea is very easy. You get your Keras model. If you know TensorFlow, you know Keras is the high-level API. We've seen like many things today. You actually create a model, you save it, you convert it with a converter, and I'll try to show you like in the next 5 minutes. And then this converter create like something that's called a flat buffer, that is simply something that you don't need to parse when you load. It's simply just the bit one after the other. You copy on the client, on this one. This is the client, your client. On this client, you have an interpreter that runs it, and then you can actually use it. That's all there is to it. I mean, basically, okay? So Keras, save the model, convert it, copy it on the client, run it with the interpreter. That's basically the main workflow that you have to do when you want to use TensorFlow Lite. And that's it. So, okay, you import TensorFlow. Good. Because actually TensorFlow Lite is in TensorFlow. Okay? Just the first is small distinction. If you run it on your laptop, you can actually use TensorFlow and TensorFlow Lite, because TensorFlow Lite is part of TensorFlow, TF.Lite. But when you run on devices, you actually install like this interpreter, because you don't need the entire TensorFlow package there, okay? But basically, you define a converter, and you say, I want a converter that will use this model, okay? This is just the location of your model, of your Keras models. You say, okay, so I'll just convert it, and this line just save the model on the disk. But basically, if you don't save it, forget that. You create a converter, you say where the model is, and you convert it. That's basically it. Okay? So there's not really much to it. Well, I'll skip the flat buffer. If you're interested to know what a flat buffer is, it's simply another optimization. Simply, you don't need to parse what you save. You just load it in memory, and that's it. Right? So that's actually the main idea. So now, we make it a bit more complicated. So we say, okay, we want to optimize the model. And then I'm starting to add slightly some more complication. For example, you can say you want to optimize the model. No. Well, you can still convert it to TensorFlow Lite without any quantization, anything at all, and you can run it. It's fine. It will be the same model. Okay, it will be slow maybe, but no problem there. You say, okay, I want to save it. Okay, do you want to limit to, for example, to float 16 times? Right? Typically, Keras is using float 32, right? You can convert it to float 16. By doing that, you already save half of the space that the memory that the model is taking. You can say, okay, yes, I can do that. Okay, and then you convert it, and it's fine, and you can run it. That's a smaller model, but that's fine. So now you can say the following. Let's say I want to convert everything to integers, right? This one wants everything integers, including the inputs. Now, let me ask you one question. I told you that when you quantize something, you need to know the minimum and the maximum, right? To map it to a linear one. But if you don't have any idea about the inputs, how can you convert that? Because you have no idea about what the inputs and the output. You could say, you know what, our image is 0 to 155. Good. But you would probably get many zeros in there. So the way that the TensorFlow Lite is using it is that, okay, you know what? Just give me a couple of examples that I can get an idea, right? What happens is you may lose some of the extreme cases, but you know what? Maybe I don't care. So typically, you give a representative data set, and TensorFlow Lite use this data set to also quantize the input, for example, okay? So you limit to integer 8, and you can actually use it on, for example, here. Or you can say, you know what, I don't have a representative data set. I don't want to give you the input. Forget it, I don't care. So that means that you can still convert it, but there are still some operations that will be floating point and some will be integers. Okay. And just to give you an idea about the speed up, 4 times smaller, you go from 32 bits to 8 bits, factor of 4, roughly 4. That's always the case. Speed up, kind of. But you can get up to that. You can even get much more than 3 times, okay? But that's just to give you an idea what actually the quantization, and when you run it on a TPU, what you can actually get, okay? And just to give you an idea how you quantize things, and I'll go, so you don't have to memorize that, you'll find examples, but you remember that you say where the model is and you convert it, and before converting it, you can say, you know what, I give some optimization options, and I want to say optimize for size, and TensorFlow does it for you, everything, okay? Or you can say, I want to convert completely, like I want to use integer 8, so you can define a representative data set. Just give 10 examples. There are examples on Google Colab that you can look at. But just to give you an idea, you just create a generator, and then you give the generator, and then TensorFlow does everything for you. Okay? And check that it's always the same pattern. Create the converter, you give the optimization variable, and then you actually convert it. Okay? But you have to convert like completely like to integer 8, meaning that you have to force that you have integer as input, integer as output, that you want to use only operations, because imagine that you have to have operations that run on TPU that are written to use integer 8. You cannot use operation that convert integers to floating point. Otherwise, it kind of loses its purpose. Right? So you need also, in TensorFlow Lite, you have like a version of each TensorFlow operation that actually runs only with integer. And that's one reason why not all operations have been written to run on integers. So sometimes, if you have special models, you cannot convert them because you don't have the integer operation. And just if you're using like 2.2, like the TF nightly, that's just a hint, you have to set that helps because they are like, it's a lot better than the old one, in case you want to play with it. So, and then, if you want to run it, of course, you can convert it on TensorFlow Lite, not yet enough. You have to compile it to run it here because it kind of gets converted to the right format. Okay, I'll show you an example. But just for you, you can actually check the slides and check the process that you have to follow. And what I wanted to show you is the following. For example, if you take, the MobileNet V2 is a famous convolutional network for image recognition, and you can download it with TensorFlow. You can actually check that the size, for example, the original one, if you load the existing one with Keras, it's like, like 14 megabytes, roughly. If you convert with TensorFlow without doing anything, kind of still 14 megabytes. Huh? You convert it, to 8-bit, it's 1/4 of space. 32 bits to 8 bits, right? And actually, if you look in the GitHub repository and you go here under the profiling folder, you find this script here. You can run it, and it will save the files, and you can actually check yourself. You can do that on your machine. You don't need any device. Okay. Just to show you that it's really true that it gets like, it's smaller. Okay? Now, I'll just show you something, then I'll show you a demo, so that maybe I'll try to wake you up. I know it's late, I'm sorry. Just to give you an idea, I had to what the MNIST is, those kind of handwritten digits that everyone is playing with, and you want to build a classifier. So If you build a very stupid network that you don't need, but it's actually good to give you an example, like 4 layers, each having 1,000 neurons, ReLU activation function, and you actually train it, you actually need just 50 neurons, 1 layer, it's enough. But I'll explain you why I chose this network. If you run it on a CPU, 1 inference with 1 image takes 38 milliseconds. On the CPU of this small thing here, if you run it on the TPU, it takes 1 millisecond. The first one is just overhead, it has to load in memory a few stuff, but it's just 1 and 37. That's the kind of difference that you can get. Okay, this model has been trained, so have been converted, quantized, and then compiled, and so on and so forth. Why anyone has any idea why I chose this kind of very stupid network that's probably is overfitting, but whatever? Anyone has any idea? Why? Or I ask you in another way. What do you think would happen if I use a network with 1 layer and let's say, I don't know, 32 neurons only? Would you see that difference, in your opinion? Of course, the question is kind of, but do you think that you would see a difference? No. So you don't see any difference at all because the matrices are so small that the CPU is exactly as fast as a TPU for those kind of small number of operations. So what I want to say is that TPU is good, but it's good for very big models, and for very small models you wouldn't see. So in the profiling, you find like those scripts, and you find 4 scripts. One, they are called like this, and one is like big NN, that is actually the dumb network, and a small one. And if you run the small one, you would see that this doesn't make any difference at all. And that's the same for GPU. Okay, if you have small matrices and small layers and small networks, you won't see much of a difference. Okay. I would say that since it's 10 minutes to 9, so what you can find in the slides, I'll just show you quickly. Are actually, I'll tell you what. So do every one of you know what Jupyter notebooks are? Right? Okay. So again, Google Colab is actually an online Jupyter notebook platform where you can actually run stuff and run on GPUs even, right? And if you know Jupyter notebook, you know what this is, right? You mix text and code. And what you can see, you can check these examples, you know, and for example, maybe I have to make it bigger. Zoom out and zoom out, and that's the wrong direction. Zoom in, it's late. Yeah, thank you. I have a Swiss keyboard that's kind of annoying with the plus, and so I'm sorry. So you actually kind of import TensorFlow, and you actually, this is the kind of, you know, that applications package in Keras you can download, like a network that are already prepared for you. That's actually very easy. So you remember what I told you? Like, okay, I create a converter that saying this model, I want to use this model. I use the experimental new converter because from 2.1 in TensorFlow, you can use the experimental new, and then I convert it, right? And that's all. And then I've converted my model. That's all I have to do, okay? And now, what I'm simulating here is what would happen on the client side when you write Python script to actually use this converted model. And what you do is actually, imagine that you create an interpreter saying, I want to use this model, okay? Easy to understand. I have to allocate tensors, meaning it has to allocate memories for the input and the output tensors and for the operations, right? I can ask the interpreter, you know what, can you give me the input details of the input? What do you expect? And you get actually the information about, for example, the kind of image that you expect, that it expects like 224 times 224 and 3 channels. Check this out, integer, not like, not floating, but you get this output in floating, because of course at the end you want a floating number, so what the TPU is doing is calculating integer and then converting with the CPU in floating point. The output is the same, an array with 1,000 classes, you know, like the ImageNet, this network was trained for 1,000 classes. Okay, so I don't want to bore you like with all the details, but you actually kind of saying, the input data is one image, and then I can set the tensor, the input, and I can invoke the interpreter, and I can get the result. Okay, that's basically it. So it's actually, I know you want maybe understand all the line now, but what I wanted for you to see is that it's actually quite easy. So there are like 3 or 4 lines that you can actually use. And this inference part, like this interpreter, and then allocate tensors, and then this setting which input is, and then invoke, and then get the tensors of the output, is actually what you do on the device. And the conversion, the first part, is what you do on your laptop or on the development machine. Okay? And actually, if you run it, if you don't see, actually, it's interesting because I would rather run something else before we get to 9. But if you run everything and if you don't quantize the model, you can run this line that is actually, this are set almost equally, just saying check if the tensors, the NumPy array, are equal within 5 decimal places, and you get actually true. So they're exactly the same result. When you convert it, you don't get any difference. When you quantize it, you will get differences because you will get different results. Okay. Just for you maybe to think about it. And then the other one are actually what I tried to build, and I hope it's going to be useful for you, is really like, instead of using MobileNet and the downloading stuff, and you don't know exactly how it's working, what I developed here was a complete example. I think is the easiest thing that you can actually do with TensorFlow Lite. That if you have done MNIST once, you've seen this like 2,000 times in 2,000 blocks. You download the MNIST, you create like a dumb network with 128 neurons. If have you used, do you know what, right? Even if you don't know Keras, you can imagine that this is just a dense layer with all the neurons, 128 with activation. Guess what is the ReLU activation function? You have 10 classes at the end, the softmax is for classification. You compile fit. This is kind of the hello world with Keras, the smallest example that you can do. And actually, in this notebook, I actually converted this the smallest example that you can do, so that you can actually understand all the point. And you can follow you can do the plane conversion without quantization, and you can see the size, and you can download it. You can convert to 8 bits, and so on and so forth. And you can actually check, for example, that the models gives you the same result. Okay, so you can actually try to follow that. Simply opening, and if you see that when you open it, you see this button, open playground. If you open like this, you cannot run cells, but if you open in the playground, you can save it on your Google Drive or simply run it and play, and you don't destroy anything. So don't worry about that. So what I wanted to show you very quickly is actually how this works, and give you a few tips. So this one, you can buy this one if you want to play with it. It costs probably $150 or so. If you have a Mac and if you have Catalina, the installation is kind of painful because Catalina doesn't recognize exactly. Yeah, the Catalina doesn't recognize it as a network connection, so a part of the installation doesn't work. In the repository, you find a markdown file where I wrote how to install it and do the same thing with Catalina if you're interested. But what I want to show you is what we are going to do is the following. I'm going to connect to this here with a serial connection. Like it was like in the 90s, like the serial connection is exactly the same. And you will see that, for example, I open like this one, and I really have to see if I can increase bigger and bigger. You know that I can do a plus, but with the Swiss keyboard is kind of annoying. Okay, so can you read it, kind of? Okay, so what you do is that if you want to try, you have like to connect to a US cable. This is just a mini USB cable. And something else that you may want to know is that not all cables are created equal. There are cables that works perfectly fine for charging your phone, and that for some reason this device does not recognize, or the laptop. So we had cases where people were actually trying with Windows, and we had to try like 5 cables until one worked. So you actually connect it, and you cannot see it, but there are lights here. And when you do it, you need to install the right driver. And if you go on the Coral.ai, and you can actually open a serial connection on the Mac. On Linux, it's the same. It creates like a device file. On Windows, you need PuTTY. If you have Windows, you can download PuTTY. And in PuTTY, you can actually define a serial connection. And there is also a link in the repository how to do that. And you open it. Okay, so what's happening is that is happening for something to come from here. This is not powered on yet. It's just a connection. So I have like a network, and probably what will happen is nothing, because sometimes at the first time it doesn't happen, so nothing happens, but we try. So you connect to the power, and in theory you should see appearing text there. And as you can see, nothing is appearing. And the reason, actually there is a reason, is that apparently there is a bug with Catalina, a bug that very often the first connection doesn't work. So what you do is you disconnect it, I'm not joking, and you have to actually kill the terminal, because if you use the same terminal, it won't work. Yep. So just in case you want to play with it, I warn you. You cannot say that I didn't warn you. So, and we reconnect it, and now it has to work, because otherwise it would be very bad. And we do that. And then we can try again. Second time works, it always works. For some reason, sometimes works the first, but very, very rarely. So there is surely some bug on the Mendel distribution and Catalina. They don't like to play together for some reason. So what you can see here is the first thing that I think is interesting to see is the name is actually a random generator name. And I remember we were actually at Google with Nick actually flashing cards, and we were actually wondering what the next name would be. You get very fun names. So if you want to spend time, you can flash it again and again and see what names are generated. The classical, the standard login is Mendel. And it actually seems like a normal Linux environment. I say seems because for some reason, for example, if you want to install like the new version of Pandas or NumPy, good luck, it's not actually working very well, because is missing actually some components that you need to compile the packages, because the packages are not yet compiled for the CPU with the last version. So you may get some difficulties, but the standard Python that comes with it has everything already installed. So you can use almost anything. Now, I have like this still the Zurich path, but it's the same repository, and you can actually go on profiling. And what I want to show you, if it's working, is, for example, let's say I take this one, that is the one for the big network. Now, what I want to show you is something. Yeah, of course. That's probably Python 3. It doesn't play well even with the when I resize the that's nice. I'll write it again. So now, what is actually doing here is actually loading. You know, the MNIST comes with a test data set that is made of 10,000 images. I load the 10,000 images because I was kind of, I didn't want to split it before, and I use one for inference. And I want to show you how long it takes to that kind of device to load the 10,000 images. If you do it on a laptop, it takes nothing. So it just, now it runs, right? So you see that it's like 38, but have you seen how long it took? So that just to give you an idea what it means when I say like a small RAM and a low CPU, it takes forever to load stuff. That's really like the speed that you get. And this one was at no TPU, so you see the 38 milliseconds, it just does like 10 times. And now I have I cannot use the back because I've resized the terminal, so I warn you. Just let me take the big one for like with mist. Now, again, I don't want to count the seconds, but it's forever. if you do that kind of thing. So it's like forever. And now you can see instead, keep in mind the 38 milliseconds. Then I want to do one small demo. You see how long it takes? Imagine having to load and saving like stuff from a webcam and so on and so forth. But you remember the 38 milliseconds? I cannot scroll back because it will not work. But you remember the 38? So this is now below 1. Okay? Because this model run on a TPU. And maybe just as a remark, is actually, again, so that doesn't look nice, but what I wanted to show you is that there is just one component that you need to do when you want to use that, and you want to use what's called a delegate, meaning that when you define this delegate, this lib edge TPU, it means that when it will check if there is operations that can be run on a TPU, it will run them on the TPU. You find examples in the repository. But just keep in mind that TensorFlow works also with what they call delegates. It means the delegate is simply a class that gets actually tasks from another one, right? So you ask, okay, can you run this operation on TPU? Yes, I can, so I'll do that. Or no, I cannot. Okay, I'll give it to the CPU, okay? But basically, you will see that it's actually quite easy. So there is not really nothing else that I haven't shown you before. So just this kind of inference step. And the last thing that I would like to show you, if you have like other 5 minutes of patience with me, and I want to show if I've like the, let me see if I find it because I would really like to show you. And those are like documentations, setup. But I have to check if that works because we need a network connection. So now what we need to do is I need to give like, because the Google Wi-Fi, sorry guys, but you have a firewall that is not playing nice with the device. So I'll use my network, and I have to put my laptop and the device on it. And I have to do it on a text base, and let's see if it works. It takes just a second to see it. Okay. Okay, now it should be activated. Now, both should be on the same network. Now I can run this. Okay. And then I can actually run 4664, and I have to go here, and let's see if it works, because sometimes network doesn't play right. And the port was exactly this one. Yes, it's working. Cool. So this is actually running on the device, okay? And this is like 60 frames per second. It's running on a TPU. This is a network. This is actually processing a video. This is just a video of cars, okay? And you see that it's actually limited to 20 cars, and it's kind of, yeah, now it's slowing down, but it's around 60 frames per second. So roughly, yeah, 10, 15 milliseconds, okay? Now I have to put that here, and if I remember correctly, if I push N, it doesn't work. Let me see. Let me do that again. So pressing N, it should. Now, okay. Now it's running on the CPU. See the difference? Like it's 2 frames per second and 370 milliseconds. So when you do that kind of stuff, I mean, it starts to get really interesting when you get this kind of possibilities. And if it doesn't crash, now it's running on the TPU. Okay? Maybe, yeah. Or maybe not. Yeah, it's running. But just to give you an idea about the difference it can make. But of course, you have to have models that can run on the TPU who has only the operations that are converted to integers and so on and so forth. Okay. Do you have any questions or something that pops to mind, or you would like to know more, or you get it? Yes.
Is there any program for university labs to apply to have TPUs or something like that?
If you ask about Google Cloud TPUs, those are different kind of things. Because what I didn't mention is that, for example, on that device, you cannot train model. You can just do inference. On the Google TPUs, yes. There are actually research grants from Google, and you can actually ask them. But I know that there are for universities like grants that you can request, and if the project is interesting enough, you get free credits to use Google Cloud Platform, for example. If you want to use those, they cost like 150 euro or stuff like that. But for Google Cloud, check the research grants because they have them. But of course, it depends on what kind of projects you're doing and that kind of stuff. Yeah. And again, so the nice thing is you would think I can train stuff on that and it will be so much faster. You cannot do that here. At the moment, you can only do kind of transfer learning a bit if you know what it is, but you cannot train stuff on this edge device. But you can train stuff on the Google Cloud. But programming TPUs on Google Cloud is completely different. So it's something different than what I showed you. This is really TensorFlow Lite and the on edge devices. Okay, you can actually run TensorFlow Lite on a Raspberry Pi. It's fine. You don't have a TPU, but you can do the same kind of quantization, make it smaller, make it faster, use less energy. You can do exactly the same on a Raspberry Pi. Okay, this is just the last part where you compile it and use the delegate, and it runs faster, but less energy, less memory footprint, and so on. Are all valid points also on a Raspberry Pi. There are like all these guys, the news. Also, I think there are many producers like IBM is one, and they produce those kind of chips that you can use to run hardware accelerators. Yeah.
Can you do a conversion? You didn't mention any type of pruning or something like that.
No, it's not. Let's say you can do that in addition, but it's not. TensorFlow is not doing that for you automatically. No, I mean, what you would do, you would train your network, you can prune it, and then once you have your like optimized model, you can convert it. Right? But I agree with you. So pruning is, if you don't know what pruning is, it means that when you train a network and the weights are so close to zero that don't play any role anymore, you can actually start to think, you know what, I can take them out and make the network smaller. Right? So that you save a network that is actually smaller, but has the same effect because those zeros will not play a role anyway. That's what's called pruning, high level, right? But it's not automatically done. But that's a valid point to make smaller networks, yeah. Anyone else? And if you want after that, if you want to see it or like to see how it works, then you can come here. So usually we have like 6 or 8 that people can try, but with this number of people, it's really hard to let everyone try it because it takes roughly 1 hour. One has to have 1 hour free to people to try cables and connect, and it's the connection. As you've seen, it doesn't work at the first time and so on and so forth. So kind of, but if you want to try some, and if you're like, you can contact me because with Google, we have like, I think that in Zurich, we have like 25 for testing. I mean, it's in Zurich, I know it's not Italy, but we could actually try to organize if one wants to do an event where people just have trying or so. And if you're interested for research or like any reason, you can actually get in touch, yeah?
Yeah, the use cases about using.
Well, typically are those kind of image recognition. You know, you can connect like the Raspberry Pi camera and just use it. But again, so it's, at the moment, it's more like, still work in progress, kind of. I mean, you can use it, but it's, for example, the documentation of this device is not completely up to date. For example, it will tell you that you need Google, like the TensorFlow 1.15. It's actually not quite true. It doesn't work anymore that well. So you need the 2.2, but the 2.0 is not working. So it's kind of a, but I guess that, for example, you could build an array and run inference on very big like images or stuff like that. It's something that you could do. Hmm? Yeah, you can use TensorFlow Lite and deploy it on Android, on iPhone. Yeah, well, on iPhone is a different thing. On Android, you can deploy it. Yeah. You can do exactly the same, deploy it on Android, deploy it on Raspberry Pi, deploy it here. You need the right delegate to take, for example, on Android, you have also some GPUs that you can use, but you need the right delegate, and depends on the model and so on and so forth. I don't know of any, but possibly it could be a possibility, yeah. I mean, you have like, when you have the device like Alexa, they just continuously listen, and you get like networks that are like few kilobytes just to be able to run so quickly. And this continues running. So basically, I'm finished, but if you have any questions or you want to check it, you can come here, so I'm happy to answer questions. So otherwise, thank you for staying with us so long.